So next presenter is Marvin Kehl. Marvin is presenting building shelters with solar sintering. Welcome, Marvin.
Hello. So before I want to talk about solar sintering, I just want to tell you about a little story and tell you about why we want to do this. And we are starting in 1977 with the launch of this little guy. This is Voyager 1. And as soon as he reaches our orbit, he sees something like this. And this is home. So this is the best living environment we know for humankind so far. And most of it we designed and fit the areas we're living in to our needs. So it's very safe and very comfortable for us. We still have some extremes, like in the poles, we have permanent ice and low temperatures. We also have deserts, which is the other extreme, where we have dry areas and very high temperatures. You can't see it so good. Do you see the red text? Okay, perfect. And the problem here is, as soon as we reach out and go into unsafe spaces, we face dangers and risk, and this can be expanded. So now we will follow Voyager 1, and we don't go this far. We are only 6 million kilometers away from the Earth now. And this is one of the earliest pictures Voyager 1 took from the Earth. And it's the first image we ever took from the Earth and the Moon together in a single image. And like what we did on the Earth, we want to look at the Moon. Is it sustainable for us? Or can we live there? And the advantages is, yes, it's very near. The disadvantages is no atmosphere. And this comes with a lot of problems. So we have the problem that water can't exist in a liquid state without atmosphere. We face problems with radiation, asteroids impacts, extreme temperatures, the list can go on. So this is a very unsafe place. And the biggest problem here is we have no atmosphere. So maybe we find something else in our sun system that has a bit better conditions, and therefore we skip time from 1977 to 1980 when Voyager 1 fly by the Saturn. And Saturn is a gas giant, and besides his famous ring, it's not very interesting for us. But what's interesting for us is Titan, the little moon. And he has a very dense atmosphere. He has also clouds and a working climate system, and it even rains, and the rain falls down, and we get liquid lakes that are toxic. So let me quickly change that. So we see a pattern here. The more we reach out of our safe space, we face problems. We have high risks in unknown territories. And this is the last picture Voyager took. At the moment he reaches out of our solar system, and he shot it 7 billion kilometers away from the Earth. And it's basically a selfie from us. What you see here is the Earth and a lot of unknown space. So if I would paint the unknown space red, you wouldn't even see the pale blue dot, which is us, because it's less than 12% of a pixel of the picture. Luckily, we are here right now. Why do I tell you all of this? The Voyager program is a good example for the humankind reaching out and collect information expand their knowledge with at least no risk for human life. No person would ever could do this journey without dying, but Voyager 1 is still out there, happily flying through deep space, and sent a picture here there to us. So the idea I have is quite comparable. So we looked at 3 examples right now, and they're quite different, but they have something in common. And this is, we can harvest solar energy, and we have ice or snow or granular medium, which is meltable. So we don't have to go that far to show you my idea. So we go back to our poles, and what I try to reach is we want to make dangerous places a little bit safer for research groups who has to go there. It's a little bit different to Voyager. This was unmanned. We're facing on a program which is manned, but in dangerous places. So if we zoom in, the idea is that an arriving research team won't see something like this, but more like this as they reach their final destination. And what we see here is basically an igloo with a spiral on it. And this comes from the idea that we want print with rovers that are automized and use the sunlight to melt snow or sand. Therefore, that we don't have a printer which is attached on a rigid frame. They have to move up and down of the printable object. So therefore, we calculated the spiral, which is therefore built ramps to give the robots the opportunity to drive up and down. And the small formula you see on the right builds this spiral with an exact width from rotation n to rotation n+1. Then we can project it on the outer surface of the sphere using the formulas on the right again, and extrude it to build the ramps for this system. The next thing I want to show you is the idea of the rovers we want to build. We want to make it very low cost, so we split the rovers into 2 task teams. So we have 1 carrier and 1 printer, and even the functions should be split into 3 different modules. The first module will be the rover. This is the moving part, which can be attached to the 2 other modules. There we have the carrying and the printing module. And what we are doing right now, because it's a very early stage of a research project, we focus on the printer module because we want to approve our proof of concept. So right now we are building the printer module, which is basically a parabolic mirror which can be automatically adjusted to the sunlight and there's no mouse, and harvest sun energy and focus it on another small spherical mirror which is attached to this and paralyze our sunlights. Sorry, okay, so which is then go down to the mirror system and can be melted the layered material below. Here at the end, this is movable so that we can print a line, and we have a lens attached to it. This lens can be adjusted, and with it we have the possibility to increase or decrease the focal point, which is needed, that we can adjust to the energy we need and the melting temperature we have to achieve for different materials. And this is the calculation you need for it. It's in comparison with the solar energy, Q solar, we have harvested, and the Q melting, which is the thermal energy we need to get the temperature up to the melting point of the given material. And if you take this, you can calculate the ideal speed of the printer according to the area which is lit up and the layer height, which is in the volume of the melted material. And at the end, I want to show you our actual model and in one-to-one, and this don't move at the actually at the speed we want to have it, but we start to move it and adjust it to the sunlight. Okay. Okay. Alex. We don't want to make bricks. We don't want to make bricks. That would imply that someone who comes there has to build his house. It should stand finished as soon as they arrive.
Can you explain the difference between this concept and the other concept we all know from that guy putting his lenses?
Okay. I think you mean Markus Kaiser. Okay. The question is the difference between this and the work from Markus Kaiser, I think. Markus Kaiser did this. Firstly, it's not movable, so we have to bring it with a cart to the desert. And second, he has a printing chamber. So he prints into the chamber like a traditional sintering process, and it's purely for artistic reasons. So this is the difference.
And you can print lines.
We hope so. Yes, the calculations say yes, but at the moment. So the last test we did with a very small Fresnel lens, which don't have the same amount. So now we use mirrors. The advantage of a mirror is that it reflects almost 100% of the sun. Not this mirror because it's not so expensive, but we used the Fresnel lens before. That is the same lens that Markus Kaiser used, and they don't have a perfect alignment. So you don't get a perfect focal point, but the advantage of Fresnel lens, they are light and not so expensive. So I think the Fresnel lens we had was DIN/4, and we still reached a temperature of 800 degrees. So this is a mirror with a diameter of 60 centimeters. So I hope we get at least 1,200 degrees with it. So, which is a little bit under the temperature we need for melting quartz, but everything else, I think, is working with it.
We have a question from Benedict.
Do I hear?
I can also ask it in person. Can you hear me, Marvin?
I don't hear him.
he's asking, he's asking how I'm going to handle with the atmospheric interference like wind.
This is a good question. Do I have to repeat it? Yes.
No.
Okay. Okay. Yes, we can go back to this. So we have a mu reduction factor in it, and as soon as we know how many energy loss we got from wind or the system itself, we can plug it into the factor. And so we can't get rid of any reductions from the environment we are facing.
Just resolution wise, like what is the limit that's going to be like how thick and how long is it probably going to take for however like the shelter is if we show it to be printed, because like the way I understood it was also that the printer is going up on what you printed earlier, right?
Yes.
So you have to wait for a certain time for it to like whatever material is to get solid. Right? So how long does it take to just
Okay. So, yes, I was just starting. The question was, how big are the layers? This was the first one. And how does it work if the melted material is printed and then the robot has to move over it? So again, we can go into the calculations. And first, it highly depends on what you print, which material parameters you have, and the temperature you need to melt the material. And therefore, we have the ideal velocity of the printer or the lenses. And therefore, then we can calculate how small or big the focal area should be. And this gives you the width and the height of the layer you will print. And as soon as this is working and you know the reduction factor, we go slightly above the melting temperature. As soon as you move on, it will be hardened. And the material which we are facing is on the minimum is ice and the maximum is melted quartz, which is a very dirty glass-like material.
So you can just instantly, like you print the first layer of the structure and then you can just instantly go up and you don't have to have a waiting.
Yes, these shelters should be quite big because they are used to give safety to people. So I think we need at least a radius of 3 meters of the domes. So as soon as the road makes a round, it's caught again. And even if you have to drive back or something, if you wait a few minutes, the temperature decreases under the melting point and the material will harden again.
You don't have to, it makes you better to have a lot of design work with this.
Yes, so the printing process is very traditional, I would say, compared to FDM printing, but the process is a little bit different because we try to get rid of the support structures and we need to move the printer a little bit different.
No, it's the same question, but
I think it was following the expressions about like wind. I think this issue is not like the direction, more like what is regards to wind and your power to look.
yeah, you said here it's a present, not
I don't know if I understand the question right, but you said as soon as you get wind into the system, the melted material will fly away. The energy, the powder is flying away. Yes, this will be a problem. Yes, all we have to, the only thing we have a lot of is time. And therefore we can think about only printing when we don't have this high wind pressure that the material will flow away.
Yeah, actually, I didn't really get the material because it's a kind of goes up, but it carries the material itself.
Yeah, the idea is, so the question was, how do we get the material up the object? So I can show you yes, we have a carrier module that carries material we need and lay down layer-wise on the igloo or dome, and therefore we need the ramp, so they still have to go up and down all the time.
And the other one is, did you think of, are you thinking to work on other applications? Because I can see.
Okay, the idea is, do we think there's already thought about other applications? No, because we still don't have a proof of concept, and at this stage I highly focus on getting it done and not spread the ideas too far.
Yeah. Because I was thinking it could be amazing for coastal protection and desertification.
Yes. But at the moment,
Yeah, you have to make a choice.
devil lies in the details. So at the moment, we focus on how can we automate the movement, and we build in very small motors so we can reduce the energy we have to have for the module, because the idea is to power it up with solar panels, but therefore we can have big motors, and the movement is very slow at the moment, or it sounds like it explodes any minute. And this is the problem at the moment.
There's a question here, how does the axis of the printing system works?
The idea is that the rover underneath will move it to its place, and we just have to give the printing module the possibility to print horizontal in this.
Yeah, next layer, the next layer.
The next layer comes with the carrier module. So the carrier module goes up.
It's fine.
Yes.
No, that's very much misdesigned or not.
No. This is what's designed at the moment.
Black box.
Yes.
Last question.
They're caught in the center, then fundamental mixing of it, but they just follow it in water and dirt, and that you can just use the same technique that your printer produces both with the each construction. That you always
So if I understand the question right, you ask if we. Okay, but okay, thank you.